Hello, everyone. Welcome to today's Wolfram Institute live stream. Today we have Jorge Alberto Lopez and his colleague Jesus Montesinos. Jesus, why don't you introduce Jorge and we'll begin.
Okay. So thank you, everyone. Thanks for coming. So our topics today is using Mathematica to solve the Dirac equation in curved space-time. So this was my mate's master thesis. It was really nice to do this because at the beginning, I would like to tell that my mate was a noob in Wolfram Mathematica. So we started from zero. We started from doing all the code, and I think it was a good experience, not just by the physical or mathematical point of view, but also learning a new programming language while doing this thesis. So I am proud of him because we did a lot. I just helped him with some easy stuff or some how to do this, how to do that, but almost the entire code was done by him. So it was really good, and we had a lot of fun. We This is like the final code that we did, but the real part is that we did like 20 notebooks before the real the real code because we were testing different stuff. So this is going to be nice, and I hope you enjoy this uh topic. So Jorge, you can start. You
Thank
can.
you very much. Hi, everyone. Thank you for inviting me. Let me introduce myself a little. My name is Jorge. I'm from Mexico. And today I'm going to talk about how to use in Mathematica to solve the Dirac equation in curved spacetime. All right. First of all, I want to start with some basic notions. You have heard about the Einstein theory, the theory of the relativity that explains almost everything in the universe, from the spectacular goal of Zlatan Ibrahimovic to the movement of the planets and the orbits, the behavior of the stars, the existence of black holes, etc. And this is a beautiful mathematical theory that uh, it's made of two theories. First, special relativity. This is the theory that explains the movement of the bodies at high velocities, at velocities close to the speed of the light. When the matter moves close to the speed of the light, uh, some strange behavior happens. For example, we have left contractions and time dilatations. And, and here we have so many famous paradox, like the twin paradox, etc. And this theory worked very nice with the theory of the electromagnetism of Maxwell. This is because in this theory, time and space are the same thing. Also, mass and energy are the same thing. What is the lesson? The laws of the physics must be formulated in a covariant form. What means that? It means that the laws of the physics, the equations that express the physics, have to have the same form in the time coordinates and also in the space coordinate. All right, keep this in mind. All right, this theory explains the the movement of the body, but we are missing the gravity. If we want to introduce gravity, we we need to talk about general relativity. General relativity is a generalization of the special relativity that introduces gravity, and the gravity is at this level become the curvature of the space-time. Here, the space-time is not fixed, it's dynamic. All right? So, with special relativity and general relativity, we can explain almost everything in the universe, but we're missing something important, something very important, the quantum world. The quantum mechanics, it's today one theory so important because in our daily life, we use the application of quantum mechanics every time. For example, to communications, to electronics, to medical device, etc. So we can't ignore quantum mechanics. And quantum mechanics, oversimplifying, it's telling us that the matter is covered by this Schrödinger equation. Look at this equation. On the left, we have a second order operator in the space coordinate. On the right, we have a first order partial equation operator in the time coordinate. There is not a covariant form. Time and space have a different form in this equation. So this is not a relativistic equation. And because of this, quantum mechanics and general relativity is not compatible. This is the big problem in the modern physics. Scientists today are looking for a theory of everything that combine general relativity and quantum mechanics. This is called quantum gravity. All right. In the last 80 years, scientists has been so many attempts to solve this, and one first attempt was the Klein-Gordon equation. If we start with the famous Einstein equation that telling us energy and mass are the same, we can remove these physical magnitudes to operators in the usual way that we did in quantum mechanics, and we can identify the energy operator with one differential operator in time, and we can identify this momentum operator with one differential operator in the space. So some notation later, we arrive to this Klein-Gordon equation. Here in this equation, we have a second order operator, second order differential partial operator in the mu coordinates. Here mu runs the time index, but also the space index. So we have the same form in the time and in the space, and second order operator. All right, this is a relativistic equation. This is a quantum relativistic equation. But there are so many problems with this equation. Particularly, we have negative probabilities with this equation, and that is terrifying in quantum mechanics. So this Klein-Gordon equation is not enough. We need another equation. Okay, in the Klein-Gordon equation, we have a second order operator, but one option is think about one first order operator, one linear operator in time and space coordinates. All right. If we regard this Einstein equation, we can see that if these are numbers, we can't have a linear relation between the energy and the momentum in the general case where the mass is not zero. So we can't get a linear relation if these magnitudes are numbers. But if these magnitudes are matrices, maybe we can factorize this equation here in this form and get this final Dirac equation where this gamma matrix, this gamma here are matrices 4 by 4. All right, I don't know these gamma matrices. I just I'm just going to suppose that exists 4 gamma matrices 4 by 4 that allow me factorize this expression. All right, but if this is happening, how can it be these gamma matrices? Well, these gamma matrices have to satisfy this Clifford condition. This is called Clifford condition because the gamma matrices form a Clifford algebra. That is a topic itself, a beautiful mathematical topic itself. I don't going to talk about that here, but these gamma matrices have to satisfy this condition. All right. Look at this equation. Here, mu and nu is running all the index, the 4 index, 1 in the time and 3 in the space coordinates. So here we have actually 16 equations, and each matrix, each gamma matrix, it's a 4 by 4 matrix. So we have 16 variables in each gamma matrix. So we have a system of 16 gamma matrices with 64 variables. All right, this is insane. Solve this, it's almost impossible. But this is a problem well known, and here this is a solution to the gamma matrices. This is one representation for my 4 by 4 gamma matrices, but there is a lot of representations. I can choose the representation that help me to solve one particular problem. All right. So far, so good. Let's summarize. We get a relativistic equation, a quantum relativistic equation that satisfies the principles of the special relativity. There is no gravity yet, all right? If we combine quantum mechanics and special relativity, will lead us to quantum field theory. The quantum field theory is the most successful theory in the modern physics today, and this theory allows to build this standard model of elementary particles, these blocks of reality, all right? The electron, the quarks, etc., the bosons. And so far so good, but we want to introduce gravity. Why we want to introduce gravity? Because it seems like the strange behavior of the elementary particles, it's manifest in a space-time where the gravity is so strong, like the black holes. A black hole, it's a space-time where the gravity is very strong. So the interactions with the black holes and the matter, like electrons, for example, give me answers about the behavior of the elementary particles at quantum level, but in a curved space-time when there is gravity. All right, but how can we generalize the quantum field theory in a flat space-time to a quantum field theory in a curved space-time? Well, we'll need to promote every mathematical object in my Dirac equation here to other mathematical objects to curved spacetimes. For example, here my gamma matrices, remember the gamma matrices? Here we have constant gamma matrices. There is not coordinate dependence here. But here we have, in curved spacetime, my gamma matrices have to have coordinate dependence. All right? There is a difference, fundamental difference. But another difference is that this differential operator, this derivative, in current spacetime, become a covariant derivative, where the covariant derivative it's made of this partial operator plus this spin connection. This spin connection is telling us how the spinor field is evolved through the manifold. It's telling us how the spinor field is changing through the manifold. All right, through the spacetime. But now, because our gamma matrices are now variables, we have to solve this system of 16 equations with 64 variables for every point in our spacetime. All right, there is just impossible to solve. Apparently, it seems like it's impossible. Well, one way to solve this is introducing the tetrads. The tetrad, it's a orthonormal frame that form a basis for the tangent space in every point in our manifold, whatever that means. The important thing is that the half orthonormal frames simplify a lot the calculus. All right. In particular, half orthonormal frames allows to get a solution for my gamma matrices with coordinate dependence, like linear combination of my gamma matrices that are constant with my tetrads here. The dependence in the coordinates, now it's in the tetrads, not in the gamma matrices. All right. And even more, we can express my spin connection in this way that it's in function only of the tetrads. We don't need anything else. With the tetrads, we have built every mathematical object that I need in this theory. That is great. That seems like an answer, but there is a problem. There is a problem. The tetrads formalis doesn't provide all possible solutions of the gamma matrices. We are looking for more solutions. Why? Well, let me introduce our case of interest. We want to solve this particular spacetimes, the spacetimes with spherical symmetry. This kind of spacetime is just one spacetime with this metric tensor here, that in the two last coordinates I have a two sphere, and in the radial and the time coordinate I can have whatever, doesn't matter. But here in the last two coordinates, theta and phi, there is a sphere in two dimensions. All right, this is a spacetime very easy to handle. This case of interest simplified the general problem of classify all the spacetimes. So we want to proceed with this case of interest. All right. If we apply, we can propose this system of tetrads, and with this system of tetrads, we can get this system of gamma matrices with coordinate dependence. Except here, right? Here it's constant matrices. It can be, but here we have coordinate dependence in each matrix here. All right, we have our gamma matrices, and with these gamma matrices, we can simplify the Dirac equation, that system of 16 equations with 64 variables, to only two two differential equations in the time and in the space here. But yeah, in the time and in the space here. We are simplifying the Dirac equation to do this pair of coupled differential equation. This is more easily to solve, but actually, in general, this equation cannot be solved analytically. Moreover, they often involve square roots. So solving this system requires significant computational power. So I want to find another equivalent system that be more easy to handle. All right. So, for example, let's take this Nariai spacetime. Here is one particular spacetime. The two equations before here look like this. These two equations here. Look at this equation. Here is the square root that I want to avoid. All right. If I want another system of solution for the gamma matrices, I need another formalism. The tetras formalism is not enough. So here I'm going to use this spin-based formalism. That what is telling us the spin-based formalism? Oversimplifying is telling us, all right, find your gamma matrices. I don't know how, but if you have your gamma matrices, you can build every mathematical object with the gamma matrices, not with the tetrads, with the gamma matrices. For example, the spin connection here has this expression. It's more complicated, but it's work, all right? Here, each of these coefficients, D, A, T, and S, is here where we have only dependence in the gamma matrices, and in the here I am derivative of the gamma matrices. Here is Christoffel symbol, but we can derive the Christoffel symbol with the gamma matrices too. So here are just gamma matrices. All right. I just need to find a solution for the gamma matrices, but not whatever solutions. No, the solutions that allow me to simplify my particular problem. All right. Yeah. Specifically, I need to solve this system of equation. All right. Okay. Here is where I tried to ask a solution to Mathematica directly. And let me show you my first attempt to solve this problem. All right, if I try to demand a solution, here is my 4 gamma matrices, my 64 variables, and if I try to get a solution, it's impossible to compute that. All right, no way to get an answer here. All right, now what can I do? All right, I want to simplify the problem, reduce the dimension of the gamma matrices. All right, I'm going to try now in 3 dimensions, right? In 3 dimensions, I can try to get an answer, but for here, again, a fail. All right, there is not a solution here neither. All right, I'm going to simplify even more the problem, reducing again the dimension of the spacetime. And now, for a 2-dimensional gamma matrices, I get an answer. All right, this is the answer, and this is the 4 of my gamma matrices. All right, what's the problem? I had an answer. I had an answer in 2 dimensions, but I need an answer in 4 dimensions. Well, here is where I have to think a lot every night, and after trial and error, I arrive to these expressions. What is this expression? Here we have block matrices, 2 by 2. There is the Pauli matrices, the very famous Pauli matrices. There are 2 by 2 matrices, and here A, B, X, and Y are also 2 by 2 gamma 2 by 2 matrices. So how how should it be A, I, B, X, and Y to satisfy the Clifford condition? Well, to ensure that this gamma matrices for a Clifford algebra, it is sufficient for A and B to form a Clifford algebra in 2 dimensions, and for X and Y to be diagonal matrices. All right. Well, it's great. I just need 2 gamma matrices in 2 dimensions that satisfy the Clifford condition to solve the problem in 4 dimensions. And that is just what I have here. Here I have my solution. I have two by 2 matrices that satisfy the Clifford condition. All right. So I propose this for the 2 by 2 blocks. This I and B for a Clifford algebra, and here X and Y are diagonal matrices. And with this, we can build these 4 gamma matrices. Actually, here is the program. Here is the program. So I propose my Pauli matrices, and I build these blocks matrices, and get finally my 4 by 4 gamma matrices. And I can check the Clifford condition here. So finally, I get my answer. Obviously, I am show you the final answer, right? I have to work a lot. I had to fail a lot to get this answer. But with this answer, I can simplify the Dirac equation to this pair of coupled differential equations, like before. But there are not square roots here. For example, in the Nariai spacetime, the same spacetime before, there is the equation and there is not the square root. All right. So I have this system of equation, and again, now I want to solve this system equation, and I ask a Mathematica solve this equation. All right. And I get this answer, but this answer is not easy to handle. There's problem here. There's theoretical problem here about the limits in the frontier of the spacetime. All right, this solution is not available. Okay, I want to try again, and I get this worst solution. All right, I don't want to bore you with the details, but after to talk a lot with my professor, finally we arrived to this conclusion. All right, Mathematica saved my life enough. Now I have to work, and let me show you this final part in my thesis. Here is my two differential equations, and here is the way to solve it working by hand. There is so many tricks and so many calculations here, but finally, we get this answer. This answer is are called frequencies of the quasi-normal modes of the space-time. It's not important, but this answer is compatible with the report with the reported literature. All right, this is a correct answer with another methodology. And this is the end of my talk, but just want to show you this code where I get every mathematical object of the theory, just propose these gamma matrices here. This is my here. This is my 4 gamma matrices. And with these 4 gamma matrices, I can build every mathematical object in the theory. What is the lesson? What is the lesson here? Let's summarize. All right. I want to solve this spacetime, this kind of spacetime. But the tetrads are not enough, so I need to build another system of gamma matrices. And first, I have not any idea to how to do that. So for every idea that I did, I needed to check the Clifford condition, for example, in the and another conditions too. But for example, the Clifford condition has to be to check, and I don't want to waste my time check one by one every idea. So this here is what mathematical was fundamental to check every idea that I was. That was like filters to notice if one idea have what has sense or not. But another lesson is that, all right, mathematical was fundamental, but it's not everything. We have to work by hand, all right? And I want to close my talk with this. And thank you everyone for your attention. And I don't know if you have some questions.
Very good application of Wolfram language.
Thank you.
Yep.
So the Schrodinger equation had a second order differential with respect to space and one first order differential with respect to time. Did that carry over to the Dirac equation?
The last part again, please.
Does the Dirac equation have a second order, have a time derivative, a second order time derivative?
All right, and here we have a 2-second differential operator in the space, and here 1 differential operator in time. All right, we have 2 options to get the same on the left or the right. Have first order operators or second order operators. The first attempt, the Klein-Gordon equation there is a second order operator, but that have problems with the probabilities. So the second attempt, the Dirac equation, here is just one. Here's just first order operator. All right. I don't know if it's clear now.
Oh, so this has one differential, right?
All right.
Okay. Another question I had was what the space-time that we're solving for. It's can you describe that?
This is space-time.
Mm-hmm. Yeah. So I guess the space-time here is like it's mostly flat except for one gravitational object at the center. Is that what this is?
All right. Yeah. We can think of like a usual sphere that evolves in time, but evolves in time, but evolves also in the radius. It's hard to interpret because here this radius is not a radius in all the cases. For example, in the Naraya spacetime, the radius, this radius, sometimes is negative. There is not negative radius in the spheres. All right. Actually, there are more like how to say it's more like a simple representation and simple idea, but actually these coordinates don't have to be a radius, don't have to be here, don't have to be angles, can it be whatever, but oversimplifying, thinking about a sphere in 2 dimensions that evolves in the time but in the radius too.
Well, that's a general metric, right? But other like special metrics, can you also make a Schwarzschild metric? It's basically like a special case of that, right?
This is a special case of right, yes.
No, the Schwarzschild metric is the special case of that, for example, right?
Yeah. For example, it's correct. It's correct. Actually, I saw some Schwarzschild black hole with this method. Let me show you quickly. Yeah, we have a Schwarzschild black hole anti-theta. We can. This is a spherically symmetric spacetime, and we can apply this methodology and get these two differential equations below here. So it's correct. We can apply this methodology to the Schwarzschild spacetime, particularly to this black hole.
Yes, that's cool. So you basically can solve or describe fermions in the presence of the black hole, right? That's
All
what
right.
it is.
All right. Basically, yeah.
And maybe like also derive Hawking radiation from it somehow, things like that, right?
Yeah, Hawking radiation and also super irradiance of the fermions. There are so many phenomena, and actually in my PhD, I looking for other phenomena that can I describe with this methodology.
Right. Well, what other methodologies people use? Like, are they using like Clifford algebra directly somehow? How do you actually do this parameterization for curved spacetime? Like, instead of modifying gamma matrices directly, trying to search for them, are they somehow modifying the algebra? Or what people are doing?
Yeah, first of all, we have to main in the Clifford algebras to, for example, this.
Mhm.
This is not free. This is the result of so many hours of studying Clifford algebras. This to notice that these block matrices, can it be a Clifford algebra, was the crucial step here, and that is using the properties of the Clifford algebra. And I want to talk also that this formalist, it's very strange. Nobody uses it because it's hard to compute here. Just the spin connection here, for example, to compute the spin connection here. Let me show you my code. All this code here is just to calculate the spin connection. And finally we obtain this. This is the spin connection. Well, this is the Dirac operator. The spin connection is right there, right there, right there. This is the spin connection, and obviously it's hard to compute, but give us freedom in the election of the gamma matrices, because the other formalists, the tetrads formalists, in the tetrads formalists you have restrictions, strong restriction. You only can represent, you only can represent orthogonal frames. All right, orthogonal frames it's very good because simplified some calculations, but it's a restriction that there is not all the solutions. So with the spin-based formalists, we have the problem that calculate it's terrified, but we have the freedom to choose between all possible gamma matrices.
I see. So if you use the tetrad formalism, you're basically like trying to fit some kind of coefficient before the gamma matrices, right? And it's not general enough, or maybe it has some limitations. And finding spin connection with this method is somehow more, I don't know, useful in the end. That's what you're saying.
Yeah, the standard for on Dewey quantum field theory in Cure spacetime is with tetrads. If you're looking in the literature, in the books, etc., even in the papers, if you're looking for quantum field theory in pure spacetime, always use tetrads. It's not usual that someone use this spin-based formalist. This spin-based formalist was proposed in the 80s, but because it's very hard to compute here, people forget it. People delete it. People doesn't have interest on use this spin-based formalist. So that is important, because remember that this quantum field theory in flat spacetime is the most successful theory in flat spacetime. But in pure spacetime, there is not a natural generalization. It's because of this what we have. Well, by one hand, the tetrads formalis with this deficient on solutions. And another generalization, it's the spin-based formalist, that it's better. Well, it's other formalist. It's not better, but give me more freedom. And there is not a natural way to generalize quantum field theory in flat spacetime. You know, there is not quantum gravity today. There is not a theory of everything. But these attempts allow us to build how can it be a theory of quantum gravity. All right. More or less.
Yeah, well, can you explain what is the actual theory here, right? Because usually people say when you have a theory quantum gravity, you have some kind of actual, well, something more like a methodology to actually make to write some kind of a Lagrangian or whatever, where you can couple your fermions with gravity or your metric. And here you're doing something different.
Yeah, this is it's called effective theory. It's a theory that works good at same scale. It's like an attempt, like how should it be? But it's not a theory of quantum gravity. It's like more like how should it be a theory of quantum gravity, and this level and this scale.
Right. By the way, I actually seen like some I don't know, some ideas, or I don't know, basically about the Dirac equation, that it's not really a quantum theory because it purely comes from geometry, so it's more like a relativistic modern quantum theory. So there's basically nothing quantum about Dirac equation itself. It's like if you ignore that there's some Planck constant in it, it's basically just purely geometric theory. So it comes from you can, for example, there's some nice discrete analogous that you can purely analytically continue to get the Dirac equation, or you can there's like a geometric algebra, obviously, and there are real Dirac equations from there when there's some geometric interpretation for spin. So there's purely nothing quantum about the Dirac equation. So you can say that when you unify the Dirac equation with gravity, you still doing just the classical theory without quantum in it. Can you say something about it? I don't know. Do you have
Of
some?
course, there is so many details to work. I like to think in this like experimental theory, experimental theoretical physics. All right.
Yeah.
I don't know if you know what I mean.
Kinda. Yeah. No. No.
Great, that was really interesting. Thanks for sharing your thesis with us.
Thank you.
Cool. Are there any questions from or comments from chat, Dugan?
Meebs is asking if this work helped you understand something better. Did this elucidate anything for you?
I haven't heard you. I'm sorry.
I'm sorry, my mic must be low. Has this work helped elucidate anything? Does this shed light on other subjects?
Jesús,
Like the
maybe-
nature of reality, maybe itself. Like, has it helped you understand something? And yeah, maybe, especially in connection with the kind of research that we're doing, that is a question that I have as well. If this could be useful in some of the stuff that we're thinking about at the institute. Yeah. Montesinos, I think you might be able to comment on that one.
Yeah, well, they are asking what, ¿cuál es la pregunta? What other theories or what other things you are understanding a little bit better once you did this. So for example, what if you have understand a little bit better quantum field theory, or if you have understood a little bit more about the Wolfram language, about programming, what have you done? What have you understand a little bit?
Yeah, basically, the behavior of the elemental particles in gravitational fields, and it's something very closed. It's something very restrictive, but it's just a few steps to a quantum gravity theory, to a theory of everything. But yet uh, there is need to work a lot yet.
So that was my follow-up question: is what would be sort of next steps for your research? What would you like to do next?
All right, yeah, good question. There is so many generalizations of this. For example, here we have a four-dimensional spacetime, but we want to build a theory of n-dimensional spacetimes for any dimension. This here is just for a four-dimensional spacetime. We want a theory for whatever dimension spacetime. All right. There is a first generalization. Also, we have this Nariai spacetime. It's a stationary spacetime. There is not rotating, and even there is not electric charge. So there is another generalization of this work. We want to describe, for example, rotating charged black holes in n dimensions. And finally, we want to solve what all spacetimes, not just this case, but every spacetime.
So
That would be cool.
yeah, like if you had two rotating objects in orbit of each other, like two colliding black holes or something, how complex would the solutions be, do you think?
Oh, I don't have idea, but I'm going to discover.
Excellent.
One question I had about where you showed the situation with 4 dimensions is to potentially think about how you could do this with non-integer dimensions. So say, for example, if you had like a 3.5 dimensions, like 3.125 or something, how that would even be possible. I think that would be something that would align with some of the stuff we're looking at.
For not integer dimensions?
Yeah, fractional dimensions.
All right. I don't have idea. Yeah. No.
Just throwing it.
That is, it's not easy that you are saying. I never studied fractional dimension in any context.
Yes, I know. This is experimental theoretical direction that I'm just throwing it out there to start getting people to think in terms of, maybe there could be something there to think about. So
all right.
Just mentioning it. Yeah.
Thank you. I'm going to keep in mind.
Great. Okay, thanks everyone. Appreciate it. That was very interesting. And yeah, for anyone here, Jorge, I think I'll also just definitely recommend that you join the Discord server. We have a really great book club every Sunday where we go into a lot of interesting topics related to a lot of Stephen Wolfram's writings. Right now we're discussing the Second Law of Thermodynamics book. So yeah, we'll just love more people to join that community, and we welcome everyone that's watched this live stream to join us there, continue the conversation. Great.
Yep. Thank you so much, Jorge.
Okay, thanks.